inverse of the exponential function that we graphed last class. I've already put the exponential function y equals 2 to the x on the screen. If you need a second to pause and write down that table and put it on the graph, you should pause your video now. And I definitely recommend having two colors handy. I did the first one in blue and the next one I'll do in red. So the graph we're going to look at next is the inverse of the exponential function. If the exponential function is y equals 2 to the x, its inverse is x equals 2 to the y. Now that might be hard to try and figure out the inputs and the outputs at first, but remember, filling out the table of the inverse of any function is actually quite easy. All we have to do is reverse the y column and the x column. In y equals 2 to the x, when the input was -3, the output was 1/8. So in its inverse, anytime the input is 1/8, the output will have to be -3. 1/8, -3. Anytime the input is 1/4, the output will have to be -2. And we can keep going down the blue table for y equals 2 to the x and simply invert or switch around all of the inputs and outputs. And then I will graph those points as well as I can. I'm going to start with the easy ones, the ones that are integers, the point 1, 0, 2, 1, 4, 2, and 8, 3. It's a little bit harder when the x values are fractions, but I can make it look the best that I can. When x is 1/2, the y would be -1. When x is 1/4, the y would be -2. When x is 1/8, the y would be -3. And you can see we keep getting closer and closer and closer to that x-axis. If I connect those points, you can really see the invert. This is the inverse of the blue graph. If I wanted to draw the line of reflection, we can really see the symmetry there, that the red graph is the blue graph reflected over the line y equals x. What we're going to do now is talk about the domain, range, and the other key points of both of these functions. And I want to remind you as you go, we've got two options. We can either talk about what we see on the graph, or we can remember that the two functions are inverses of each other. So when the domain of an exponential that we saw last class is all real numbers, and the range is only positive numbers, if I take a look at my red inverse of that function, I can see the x values never quite get small up to 0. Right here we're approaching x equals 0. And the x values are everything going on bigger than that forever. So the x values of my red inverse function would be everything from 0 to infinity. But the range, because this arrow points down forever and this arrow points up forever, it looks flat, but we'll talk more about this later. It's not really flat. That means the range would be all real numbers. And what I want you to notice is that the two are reverses of each other. The whole point of an inverse is the x and y flip around. So the domain, which was talking about the x values of 2 to the x, is going to have to be the range, the y values, of its inverse. The domain of the inverse function from 0 to infinity is the range of the original function y equals 2 to the x. Those things go together, and we'll see that'll keep happening throughout the rest of this little investigation. Going back to the y equals 2 to the x, if we look at the x-intercept, we can say that there was none. Because remember, the exponential function never actually gets down to 0. 2 to the x can never be 0. 2 to raise to a power is always something. But the y-intercept was 0, 1. Taking a look at the inverse function, x equals 2 to the y, that's flipped around. The x-intercept is 1, 0. Notice how that is the x and y from the y-intercept of y equals 2 to the x, flipped around. But there is no y-intercept on my red function because there was no x-intercept on my blue function. We take a look at the asymptotes here. You can see that the exponential function has this horizontal asymptote at y equals 0. I'm writing it as y equals, so you know it's a horizontal asymptote. But the inverse of that function, x equals 2 to the y, has a vertical asymptote at x equals 0. So again, what happens to the y from one function happens to the x for its inverse function. And lastly, this one's a little bit trickier. We saw this last class for the first time ever, that end behavior on one side can be infinite, on the other side can be finite. So let's see if I can find a way to fit this all in here. As x approaches infinity, I'm going to write 2 to the x approaches infinity. And as x approaches negative infinity, 2 to the x approaches 0. I used 2 to the x. I'm about to regret doing that because I didn't want to call it y. I've got two y's. And then for my red function, I've got a slight problem here. I can't use the same notation as I did before, but I can still say my end behavior, it's going to be flipped around from the last one. Now, if I take my x and my y and I flip them around, if one approaches infinity and the other one approaches infinity, well, that's the same thing. As x approaches infinity, I can't call it 2 to the y. That doesn't really work. That's my x value. So I think I'm just going to call it f inverse approaches infinity. And this one, if I flip everything around, I take this y value from the original function and this x value from the original function, and I flip them around. As x approaches 0, f inverse, the inverse of my exponential function, will approach negative infinity. So what I really wanted you to see there was how at every step of the way in that little investigation, the x and the y from 2 to the x are completely reversed when we talk about the inverse of 2 to the x. Okay. Let's look more closely at that inverse function. We know y equals b to the x is an exponential function. I used the number 2 in our example just because that's the easiest number to quickly multiply, but really it could be any base that's bigger than 0. Its inverse that we just graphed is x equals b to the y, right? That's a great inverse function. If I graph that on Desmos, no problem. But we do know from other things that we've seen before that I don't really like writing an inverse function as x equals b to the y, because what I really want to do is I want to be able to get y by itself. And we've seen this before. If I had the function y equals x squared, that's the parent function for quadratics, and I take its inverse, x equals y squared, and if I wanted to undo that and get the y by itself, we know what to do. We have this thing called a square root that we can do to both sides. And so we can say that y is equal to the square root of x. We have that example. The idea of a square root, well, that's some term and symbol that was made up because we wanted to be able to get the y by itself when we had the inverse of a quadratic function. Well, we need to do the same thing today also. We need the name of a function, a new type of function, to get the y by itself.